we have it. This is our antiderivative, and after rewriting using a trig identity, we're able to find it. Let me quickly find the antiderivative over here as well. This will be the natural log of the sine of x. Notice the absolute value. Domain of logarithms only includes positive inputs, so we have to make sure that that is so. And of course plus c. So we found both antiderivatives lickety split. Now, if you had a hard time with tangent squared, thinking that it was somebody's derivative, this would be for you to do some quick recall. The derivative of tangent is secant squared. Let's go from secant. Secant's derivative, and these would be great flashcards to make. Just flip them over. You could call them derivative flashcards, or using them in the other direction, you could call them antiderivative flashcards. Secant has a derivative of secant tangent. What about cotangent? These are some that maybe we haven't used in a while, and then we kind of forget. Cotangent being a cofunction. Remember, those cofunctions have negative derivatives. And this one would be negative cosecant squared. So likewise, we go backwards. The antiderivative of cosecant squared, if it's negative, is cotangent of x. Let's also recall cosecant has a derivative. It's also negative. It's cosecant cotangent. And all the fun ones, we've got like antiderivative for 1 over 1 plus x squared. Let me see if I can just move the whole thing. Of course I can't. 1 over 1 plus x squared is not the function we're going to take the derivative. I'm going to try to go backwards on this one. Okay, make it work. This would be the derivative for the tangent inverse function. And how about some of these other functions? Do you remember these? Well, I hope you remember these because they're going to be coming up in a video shortly. So this is the cosine inverse of x. And of course, both of these can be represented. Both of these could be shown with some sort of u sub. And that's a little harder to divulge. So you will have me as your coach to kind of get through that. What about the trig identities? This one's the most popular one. So this is for rewriting purposes. The Pythagorean identity that says cosine squared plus sine squared equals 1. That is true for all values of x. We worked with tangent squared plus 1 equals secant squared. A little manipulation of that, of course. We isolated the tangent squared, and then a third derivation. So all of these could be kind of worked from that first one, if that's the only one you know. Here we've divided everything by cosine squared, if you can imagine that. If we were to divide everything by sine squared, we would be getting cotangent squared plus 1 equals cosecant squared. And these could come in handy, especially when you get that feeling like, oh, I don't know this antiderivative, there's nothing at all I can do. Try to rewrite it with one of these identities. On this slide, we are going to talk about calculus-friendly looks. So certain functions presented in one way or the other may be easier or harder or even impossible, it seems, to work with until we do some rewriting. So when we consider each of these pairs, I will point out to you that they are equivalent, hopefully equivalent to the best of my abilities, but one is just going to be easier to work with than the other. So when we see a root function, negative 1 over the square root of x cubed, for example, some people will think that's a logarithm when we're taking the antiderivative, but no, it's just a power. So this would be the more calculus-friendly way to look at it, I would say, where we write it as a power, a fractional power. Then you just kind of go the reverse of the power rule. Here we have a fraction, and there was something kind of like this on the final exam, and people tried to do a u sub because the denominator had a higher power than the numerator, but really it wasn't exactly the derivative that was present there, so it was a strange manipulation. Here again, though, it would be easier to rewrite it and actually divide each part separately. I'll show it over here. And then write it in a simpler form. So we have x divided by I'm sorry, minus 1 over x, and that would be easier, especially when we think about antiderivatives or even derivatives. This would be easier to work with than like a quotient rule. Here's one that came up in a practice set, sine over cosine squared. Now this could be done with a u sub, so you could leave it this way. We have a u in the denominator and we have a du in the numerator. But if you do a little bit of rewriting and just take the parts of this fraction, so I'm factoring it in a way, and this still represents sine over cosine squared. We see we have tangent and secant. To me, this is easier to look at. To you, you might see the u sub, and coincidentally, when you work it out, it ends up being exactly the same antiderivative if we were trying to integrate. It looks like they're all going to be on the right side, right? Everything is going to be this or that. It's always going to be the that. No. On this one, cosine of 2x is probably going to be easier to work with than cosine squared minus sine squared. Both of those will require some sort of chain rule, and we do not have derivatives of inside functions showing there. So maybe you didn't know this, but cosine of 2x is the same as cosine squared minus sine squared. And that's an identity that probably wasn't taught to you in your pre-calc class, but we just didn't have time to show you all the identities that exist. But let me just convince you of that real quick if you want to know if that really is true. This is called a double angle identity. So we're going to do cosine of 2 times pi over 6. Basically, that's cosine of pi thirds, and the cosine of pi thirds is supposed to be 1/2. Let's make sure that works out. So if I take the cosine of pi 6, which is the angle that's been doubled here, and I square that ratio, and then I take the sine of pi 6, and I square that ratio. Let's see if we really do get 1/2. I'm running out of room, but I do know cosine of pi over 6 is square root of 3 over 2. I could square that and I should get 3/4. And the sine of pi 6 is 1/2. If I square that, I get 1/4. So 3/4 minus 1/4. Go figure. It's 2/4 or 1/2. Isn't that pretty neat? Yes, the double angle identity worked here for cosine, and you could really pick any angle in the world that you wanted and try it out. You could even pick like 13 degrees. It should work out if you double that angle. You will get the same results by squaring the cosine and subtracting the square of the sine ratios. Okay, maybe this is new to you. Write it down. Sine of 2x, or 2 sine of x. In this case, I would say either one is actually pretty calculus friendly. They both will work out with the same amount of ease, in my opinion. So you could choose either one, but maybe you didn't know that either. The sine of 2x, another double angle identity, is the same as 2 sine of x times cosine of x. And this last one is the Pythagorean identity. Do we know the antiderivatives? That's what I'm going to think about for either one of these, and I would say probably the cosecant squared is the form of this expression that we know better in terms of antiderivatives. So choose wisely, pick a form, write it in a form that works best for you if you're going to find the antiderivative. Here we're going to work on rewriting an integral using 2 possible u subs. This expression is given. Notice we have boundaries, so I would expect there to be a numerical answer. And how will we find it? Well, let's look at 2 possible approaches. If u is tangent of x, then it's always important to think about du. Du would be secant squared of x. Wonderful. And that's wonderful because we see that in the expression. So I'm going to do my rewrite. This will be u du. And these boundaries should be changed because the boundaries currently are for x. And when we rewrite with u, we should rewrite with boundaries of u as well. And so if u equals tangent of x, then this boundary will be u equals tangent of pi over 4, which hopefully we know is 1. And the other boundary will be the tangent of pi, which is 0. So we have two new boundaries and an integral set up with u. We'll do the same thing, but we'll use a different u substitution here. So if u were, let's say, secant of x instead, then du would be secant tangent. And looky here, that would still work. So we would have an integral of u du, because this time the u was one of those secants, and then the rest of it was the du. And our boundaries would be a little different, though. We would have the secant for this boundary, the secant of pi over 4, which is square root of 2, hopefully a value you know, and the other boundary would be secant of pi. So here's pi on the unit circle, -1, 0. The reciprocal of -1 is still -1, so we will go from square root of 2 with this u substitute to -1. For the last part of the video, we're going to be doing two integrals, and these are kind of not so obvious. Definitely not going to be a u sub for the first one. So if it's not u sub, well, I take that back. It is u sub. It's not an obvious u sub. This first one is going to be an inverse trig problem. And usually we're used to seeing inverse tangent set up as x squared plus 1. Now don't be distracted by the x squared and think you can just add 3 or something to get the 4. Our real goal here is going to be to rewrite with something squared plus 1. And that will be our u sub. So to get the u, I'm going to have to get the 1 first. So to manipulate 4 here, I'm going to divide by 4. Now this is only allowed if I divide every single thing by 4, keeping it equivalent. So I have 1/4 dx, and then I have x squared over 4 plus 1. That's what we wanted, plus 1. And that means what was squared? Well, there's some quantity here being squared. It's a fraction. There's definitely x being squared, and 4 is the result of 2 squared. So that is our u. And if that is our u, then du is 1/2. Notice there's a 1/4, so I would have to do half of a half to get a 4th. Here's our final rewrite. We have 1/2 of du over u squared plus 1. Take a look again. We had to multiply our du, not so easily seen here because of my handwriting, by a half to represent the 1/4 dx. And that factor I bring out in front. I like to bring out my constant multipliers in the front of the integral to simplify the process. And that means we have 1/2 tangent inverse of u. To finish evaluating, you can either change your boundaries from x to u, or what I'm going to do is switch back to x and then keep the boundaries the same. So I'll be doing 1/2 tangent inverse of x over 2. I rewrote it with x. Evaluating from -2 to 2 gives us the results. Tangent inverse of 1 minus 1/2 tangent inverse of -1. Don't get too excited. These are not complete opposites, I don't think. If I move to the last line of work here, we will have half of, this is pi over 4, so pi over 8, minus, tangent is -1 in that second quadrant, but also in the fourth quadrant, and that means I have a negative pi over 4, so minus a negative pi over 8 when we take half of it, means we have 2 pi over 8, we're adding now, and the final answer is pi over 4. The u sub needed to be done, but it wasn't so obvious until we got that 1. The very last problem I would like you to try to set up, notice that it looks like inverse trig, but it is not. This is another problem where you'll need to do a u substitute. And again, it is not inverse trig. Try that one on your own. Maybe pause the video, and I can definitely check that for you when you come to see me in person. Thank you for watching the video. I hope you learned some things about rewriting and representing these integrals in ways that are easier to evaluate. Mrs. D, signing out.